Good day, everyone. This is lecture 1.5 of Math 21. These are our goals. At the end of this series of videos, students are expected to be able to show using the intermediate value theorem that a given function f attains a particular value k, to use the squeeze theorem to evaluate certain limits, and to evaluate limits involving trigonometric functions, especially indeterminate ones. Let's begin. In the previous lecture, we learned about continuous functions. Now, in this course, we will discuss several important consequences of a function's continuity on an interval, such as results on maximum and minimum values of a function, and the fundamental theorem of calculus, which relates antidifferentiation and computation of area. But those are subjects for another day. Today, we have the intermediate value theorem. Suppose f is continuous on the closed interval AB. This means that its graph is connected from the point where x equals a to the point where x equals b. And suppose that f of a is not equal to f of b. Let's illustrate this. Now, suppose further that k is a value that's between f of a and f of b. And consider the line with equation y equals k. Now, now question. Is it possible that the function f is continuous on the closed interval AB, yet its graph does not intersect the line with equation y equals k somewhere between x equals a and x equals b? Okay. So if we try to avoid that segment by, say, having this jump discontinuity here, then we violate the assumption of continuity. Now, what's another way to avoid crossing that portion of the line between A and B? Well, if we do this to avoid that portion, then sure, we avoid the line y equals k between A and B, but then now what we obtain does not represent a function. So here actually we realize that because the function is continuous on the closed interval AB, its graph must intersect the line with equation y equals k somewhere between A and B. Meaning there is a value c between a and b at which the value of the function is equal to k. And that is the conclusion of the intermediate value theorem. For every k between f of a and f of b, there exists c between a and b such that f of c equals k. And this is true no matter what the value of k is. For instance, for this other value of k, we have this corresponding value of c, for which f of c equals k. So the intermediate value theorem says that if f is continuous on the closed interval ab, and the values of the endpoints are different, then the function passes through all the intermediate values between f of a and f of b. Make sense? Now, note that the continuity of the function on the closed interval AB is required. If it's not continuous, then the graph of the function may avoid the line y equals k in our illustration earlier. So in general, the theorem does not work for discontinuous functions. Also, the value of c in the conclusion of the theorem may not be unique. No? The graph, if the function is continuous, then the graph may intersect that line y equals k more than once. Let's have an example. Let's show that the graph of f of x equals x minus 1 over x intersects the line with equation y equals 1/2 at least once between x equals 1 and x equals 3. And we're also asked to find the value of c between 1 and 3 for which f of c equals 1/2. So we want to show that the function's graph intersects the line y equals 1/2 somewhere between 1 and 3. So it seems here that we must apply the intermediate value theorem to this function and the closed interval 1, 2, 3. So we check first if the conditions of the IVT are satisfied. So first, is the function continuous on the closed interval 1, 3? Well, the function is a rational function that is undefined at 0, so it is continuous on the set of real numbers except 0. And in particular, it is continuous on the interval 1, 3. Next, we evaluate the function at the endpoints. What is f of 1 equal to? F of 1 is 1 minus 1 over 1, or 0, while f of 3 equals 3 minus 1 over 3, or 2/3. So to illustrate, f of 1 is 0, while f of 3 is 2/3. And we know that 2/3 is greater than 1/2. Okay? So taking k equals 1/2 now, we note that 1/2 is indeed between 0 and 2/3, which are the values of f at the endpoints 1 and 3. So, as in our illustration earlier, because the function is continuous, we know that its graph should indeed cross the line with the equation y equals 1/2, somewhere between 1 and 3. Okay, that is our conclusion. Because f is continuous on 1, 3, and 1/2 is between the values at the endpoints, then by the intermediate value theorem, there exists c between 1 and 3, such that f of c equals 1/2. Now, we are also asked to find the value of c. So in this case, we just solve the equation f of c equals 1/2. So we have 1/2 equals c minus 1 over c, and multiplying both sides by c and 2, we obtain c equals 2c minus 2, which gives us c equals 2. And indeed, when you substitute 2 to this function, you have f of 2 equals 2 minus 1 over 2, or 1/2. And indeed, 2 is between 1 and 3. So in this example, we were able to solve the equation f of c equals k. So we did not actually need the IVT. Now, the power of the theorem is better demonstrated when this equation is difficult to solve. For instance, let's show that 3x to the fourth minus 4x squared plus 5x minus 1 equals 0 has a solution between 0 and 1. Now, trying to solve this equation using methods from high school algebra, such as factoring or the rational theorem, would not work. And in fact, it's difficult to find the solutions of this equation. But in this item, we are not asked to find the solution anyway. We are just asked to show that there is a solution to the equation between 0 and 1. And that is where the intermediate value theorem comes in. Now, from the item, it seems that we must apply the intermediate value theorem to the function f of x equals this expression, and the interval, and the closed interval 0 to 1. Okay, and we want to show that f of c equals 0 for some c between 0 and 1. Again, to illustrate, we want to show that the graph of the function intersects the x-axis somewhere between 0 and 1. So again, let's check if the conditions of the intermediate value theorem are satisfied. Is this function continuous on the closed interval 0, 1? Well, yes, because it's a polynomial function. So first condition is satisfied. Next, let's check the values at the endpoints. F of 0 equals -1, while f of 1 equals 3 minus 4 plus 5 minus 1, which is 3. So we have that f of 0 equals -1, while f of 1 equals 3. And note that 0 is between the values at the endpoints. Sorry, is between the values of f at the endpoints, -1 and 3. So again, because the function is continuous, we are sure that its graph must intersect y equals 0 somewhere between 0 and 1. And we write by the intermediate value theorem, there is indeed some c between 0 and 1 such that f of c equals 0. Again, note here that we were not able to find the solution. We were just able to show that there is a solution between 0 and 1. And that concludes this portion on the intermediate value theorem.